Have you ever taken a pill for a headache and just stopped to think about it? How in the world does that tiny thing navigate the massive, complex maze of your body to find the exact spot that hurts? Well, today, we're going on that journey. We're going to follow a single pill from start to finish and see how it actually gets the job done. Yeah, this is the classic question, right? How does that ibuprofen know to go to your head and not, say, your ankle? Well, here's the spoiler. It doesn't. At all. That pill's medicine actually goes everywhere the blood flows. The real magic isn't about the navigation. It's about what the drug does when it arrives. And this entire process is run by two big ideas. Meet the two main players in our story, pharmacokinetics and pharmacodynamics. It sounds complicated, but it's pretty simple. Pharmacokinetics is all about what your body does to the drug. Think of it as the journey. Pharmacodynamics is what the drug does to your body. That's the action, the job it performs. Let's start with the journey first. Okay, so you've just swallowed a pill. Its absolute first mission is to get into your bloodstream, which is basically the body's superhighway system. But here's the thing. Not all of it is going to make it. This very first challenge is something called bioavailability. Bioavailability is really just a fancy term for a drug's success rate at getting into the game. It's the percentage of the drug that actually makes it into your bloodstream to do something useful. So if you take a 100 milligram pill and only 70 milligrams get into circulation, its bioavailability is 70%. The other 30%, well, it gets lost or filtered out before it even has a chance. So what determines that success rate? Well, a bunch of things can change how much of a drug gets through. For example, having more blood flow to your gut helps your body absorb it faster. That's a plus. But on the other hand, if the drug doesn't dissolve well in water or if it gets broken down too early, less of it gets in. But probably the biggest hurdle of all is the body's main security checkpoint, the liver. And this first check is so critical, it has its own special name. It's called the first pass effect. As soon as a drug gets absorbed from your gut, the blood that's carrying it has to make a mandatory first stop at the liver. And the liver is like a toll booth. It immediately starts to break down or metabolize a chunk of that drug. So a portion of it is taken out of commission right away. This is exactly why doctors have to calculate a dose that's high enough to still be effective after this toll has been paid. Okay, so our drug has paid the toll. It's made it into the bloodstream. Great, but it can't just hang around forever. From the moment it gets in, it's on a ticking clock. And we measure that clock with something called a half-life. The name for this one pretty much says it all, right? A drug's half-life is simply the time it takes for your body to get rid of half of it. This whole process is managed by the liver, which continues to break it down, and the kidneys, which are in charge of flushing it out. So a drug with a short half-life gets in, works fast, and gets out fast. A long half-life means it sticks around in your system for a while. Let's just walk through this example here. Imagine a drug with an 8-hour half-life. At hour 0, you're at 100%. After 8 hours, one half-life, you're down to 50%. Makes sense. But after the next 8 hours, you're not at 0, you're at 25%, then 12.5%, and so on. It's not a straight line down, it's a curve. And this is why your prescription might say, take every 4 hours, or just take once a day. It is all about the half-life. All right, so far we've covered pharmacokinetics, the journey, what your body does to the drug. Now it's time to flip the script. The drug has survived the journey, it's in your system. Now what? How does it actually do anything? This, my friends, is pharmacodynamics. This brings us right back to our original headache question. See, drugs work by hitting very specific targets. Most of them work on the surface of our cells, kind of like a key that fits a very specific lock on the outside of a door. But some drugs are different. Some have like a master key that lets them get inside the building itself. So how do they pull that off? Let's take a look at a really common anti-inflammatory drug, prednisone. It's a type of steroid, and its chemical makeup gives it a very special superpower. It can get past the cell's normal security or supply. You can think of prednisone as a kind of secret agent. Because it's a corticosteroid, it's small and fat-soluble, which lets it slip right through the cell's outer wall. And once it's inside, it doesn't mess around. It goes straight to the command center, the cell's nucleus, and binds to receptors in there. By doing that, it directly changes the cell's marching orders, telling it to stop making so many inflammatory proteins. It works from the inside out. So that's one strategy. Get inside the command center and change the plans. But what about a more direct approach? Let's look at another very common mission for a drug, just stopping a bad process from happening in the first place. For this one, let's use maybe the most famous drug on the planet,
aspirin. Aspirin doesn't need to do anything as complicated as getting into a cell's nucleus. Its strategy is much more straightforward. It just stops the problem at its source. But how?
The answer is actually beautiful in its simplicity. It basically just gums up the works of a very specific little biological machine called an enzyme. So picture a tiny factory in your body called the COX enzyme. This factory's only job is to churn out these things called prostaglandins, which are the chemical signals that create pain, inflammation, and fever. What aspirin does is it just walks into that factory and shuts down the assembly line. Permanently. No working factory means no pain signals. And that's why aspirin doesn't know where your headache is. It just travels everywhere through your bloodstream, shutting down these little pain factories all over your body, including the ones in your head.
So let's do a quick mission debrief. On one hand, you've got prednisone, the secret agent that goes deep inside the cell to change its instructions. And on the other hand, you have aspirin, the saboteur that works from the outside to shut down a problem factory. Two completely different strategies, both achieving a helpful effect.
And that's really the whole story, isn't it? From getting into the system to actually getting the job done. Every single medicine you take tells this amazing story of kinetics, the journey, and dynamics, the action. So the next time you take a pill, maybe you'll think about it a little differently. Think about its incredible journey, surviving your gut, paying the toll to your liver, racing against its own half-life clock, and finally finding its molecular target to complete the mission. Now that you know the basics, what other drug secrets are hiding in your medicine cabinet?